All right, here we go. Advanced Math 8. This is the last lesson for the semester. We get to go on winter break. All right, so lesson 5.3.3. Comparing sequences and functions. A lot of these comparisons we've already looked at, but we're just going to formalize our knowledge at the end here of this part. So we're going to start with question 114. We're going to look at the sequence -5, -1, 3, and 7. We're going to create a table, create a graph, and then make an explicit equation for the sequence. So here we go. All right, so looking at the sequence, it looks like from here to here, looks like we're adding 4 each time. So it looks like our common difference is 4. So if I were to do a table, remember the sequence number goes up top and it always starts at 1. So in this sequence, our first term, so our nth term of the sequence, our t of 1, would end up being -5, then -1, because we're adding 4, and then 3, then 7, and then finally we'd get 11, and of course it goes on forever and ever and ever. So there's my table. Now we need to do a graph for it. Okay, so let's do a graph. Purple for graph, because so here we go. Go to our paper. Is my purple dying? I hope it's not. I don't like purple. There you go. That worked. I don't know, right about here. That look good? Maybe here. So our x-axis is going to be the term number, and our y-axis is going to be the actual terms. So our first term is at -5, so 1, 2, 3, 4, 5. Our next term is at -1. Our third term is at 3. The next term after that would be at 7. And then our next term after that would be 11. All right, so there's our sequence. We know at this point that we're not going to make it continuous. We're going to keep it discrete just like that, because we know that our term numbers can only be positive integers. Okay, so we've got our table, we've got our graph. Now we need an equation. All right, so we want an explicit equation. So the explicit equation is going to be t of n equals, okay, our common difference of 4, and then n, and then we have to find out what our 0th term would be. So since we're adding 4 going this way, to find our 0th term, which doesn't exist, we're going to subtract 4 going the other way, so we would get -9. So there is our sequence. We can double check to see if it works just by plugging in our term numbers to see if we get the terms. So if I plug in 5, 20 minus 9, 11 works. If I plug in 4, 16 minus 9, 7. Yes, it's working. All right, so our question now is 400 a term in the sequence? So if I keep on writing out my terms, will 400 eventually be one of those terms that I write down? Well, let's find out. Our term numbers are t of n. So instead of t of n, I'm going to plug in 400. And I get 4n minus 9. So I would add 9 to both sides, and I get 409 equals 4n. Okay, so now I'm going to divide. So 4 goes into that once, 0, twice. Ooh, we're going to get extra numbers. I need extra parts here. So 102.25 because I had a remainder of 1. So we're going to say no. Why is it no? I got an answer, but my answer is not a positive integer. If it's not a positive integer, this will not show up in the sequence. Only when the term number is a positive. There is no 102.25 term of the sequence. It just doesn't exist. So no, the term number is not a positive integer. Sweet. All right, next, we're going to create a table for the graph of the function f of x equals 4x minus 9. All right, so if I did a table of this one, we'd have our table of x and f of x. And then we'd usually just start plugging in values. So 0 gives me -9. 1 gives me -5. 2 gives me -1. 3 gives me 3, and so on and so forth. And it's pretty much the exact same, list of numbers that we did for the sequence because their equations are very similar here, except one is a sequence and the other is a function. So let's graph them, and let's see if the differences between the graphs. So when we graph this, we're going to call it the x-axis just x, and the y-axis is f of x. So on this one, my y-intercept is -9. 1, 2, 3, 1, 2, 3, 1, 2, 3. And then I've got -5, then -1, then +3, and then 2, 3, 4, 7. 1, 2, 3, 4, 8. Fit. All right, so I would go ahead and make this a continuous graph. Because in a function, I could have 0.5 as an x value, and then it would have a corresponding y value that matched it. It would work. So how are these two different from each other? Well, first of all, I noticed that t of n is discrete. And f of x is continuous. Is it because of the actual equation? No, it's because of the situation that we're in. In this situation, we're looking at a sequence where the term numbers can only be positive integers. This situation is a function where the x values can be anything. In fact, in this one, we would say that our x values are all real numbers. So our biggest difference between well, not our biggest, but one of our differences between a sequence and a function is sequences domain values are limited to being only positive integers, whereas functions, their domains don't have to be limited to integers. All right, is it possible for f of x to equal 4x minus 9? Seriously, you're going to do announcement? Okay, good. All right, so is that possible? Yeah, it's pretty much the same equation that we had here, and x could be 102.5, or 25, sorry. And if I plug in 102.25, I would get 400 for f of x. My input could be 102.25. So yes, with an input of 102.25, you would get an output of 400. The output so functions don't have the same restrictions that sequences have. The graphs look pretty much the same, but this graph here has restrictions, being that the domain is only going to be positive integers. All right, 115. So let's say I had a function that was 2 times 3 to the x power, and then I have a sequence that is 2 times 3 to the n power. It's asking, are both of those functions? Well, let's go ahead and look at the graphs real fast. So I'm going to pull out Desmos, my graphing calculator over here. And let's turn this one on. Why isn't it letting me turn it on? For some reason, it wasn't letting me do it for a second there, so let's see if it's doing it now. So y is equal to 2, and then I'm going to do the little, now it won't let me do it again. This is killing me. All right, I'm going to have to pull it to the other screen and then pull it over. So, all right, Loom's really freaking out on me, but I think I've got it to work now. 2 times 3 to the x power, I believe it was. So to do to the x power, 3x to the x power. All right, so it graphs it for me here. So is this a function? Yeah, it looks like for every x value that I plug in there, I'm going to get a different y value. If we looked at a vertical line test, we'd probably say, yeah, that passes the vertical line test. So is it function? Yeah, sure it would be. Now, if this were a sequence instead, would it still be a function? Yeah, because the sequence would just have points on this line. And of course, they would only be the points that are integer values for the x values. But yeah, it would still be a function. So I think that we can say, yes, we're definitely going to have a function there. So yes, they would both be functions. For every x value, there is only one y value. So we're not doubling up on any of our x values. All right, is it possible for f of x or t of n to be equal to 1400? Now that's an interesting question. So we're saying, what if this were 1400? Let's see if we can find out if this would work. So 1400 equals 2 times 3 to the x power. All right, so if I divide both sides by 2, I would end up with, so I'm going to divide this side by 2 and this side by 2. I would end up with 700 equals 3 to the x power. All right, let's just play around with our calculator a little bit. So, clear. So let's say that I did, let's see, 3 to the 5th power. So 3, and then this little caret button does to the 5th. 3 to the 5th power ends up being 243. So that's not 700. Let's try 3 to the 6th. 3 to the 6th power ends up being 729. Okay, so what it looks like here is that this could not be an answer if it was a sequence, because it doesn't look like I would have an integer value, because remember our exponents here are what we're looking for. So it looks like my integer values would not work. So this could not be a sequence. It can't be t of n. Because I looked at 5 and I got 243. I looked at 6 and I got 729. So we're way too much. We're in between there. But could it be a function? And yeah, we can do other exponents. Let's do like 3 to the 5.8 power. 585, not quite 700. Let's try 3 to the 5.9 power. Ooh, getting closer. 3 to the 5.95. 690. I'm really close at this point. 3 to the 5.97. I went too far over. But you can see here, yeah, we're going to eventually get there. I can use decimal answers, maybe 9.6 or 5.96. Probably it's going to be a little bit less than that. But yeah, I'm getting closer when I type in different numbers. So yeah, I can, with f of x, get an answer. It's not going to be an integer, but it's possible. So f of x would be able to equal 1400. but T of n would not be, because we found out using our calculator that I would not get an integer value. It'd be 5.9 something, so it wouldn't have worked. How are the functions and sequences similar? Thinking about it, their graphs are pretty much the same graphs, so their graphs are similar. So graphs are similar. Their equations are really similar. Okay, that's pretty similar. How are they different? Their domains are different. And if you look at the graphs, the one thing that's different on the graphs is the discrete versus the continuous. All right, let's get over to our second page of our notes. Now, before you get to the second page, it probably would be helpful to read the methods and meanings section in the book. And I've got that right over here. So methods and meanings talks about a different type of notation for a sequence. And this is actually the notation I'm used to. So it uses, instead of T of n, it uses A sub n. So this is just a different way to write it. These two would be the same thing. T of n equals or A sub n equals. So that's just a different type of notation. Here you can see a recursive process where we've got T of 1 equals 3. This one would just say A sub 1 equals 3. So it's just a different type of notation that we've got here. You know, T of n plus 1 is the same thing as A of n plus 1. So it's just a different type of notation. It's actually the one that I'm more used to using. So anyways, let's go back to this. So we're going to use that type of notation for these next couple of problems. So we're going to write the first 5 terms of this sequence. Well, the first term would be when n was 1. So this is 1.5. So 1.5 minus 1, so the first term would be 0.5. Second term. Well, it looks like my common difference here is 3 over 2. That's 1.5. So that means I'm going to add 1.5 each time. So I can just add 1.5 to this and get 3 as my next one. I'd get the same answer if I would have plugged in 2 there. I would have gotten 3 minus 1, which would, oh, this is supposed to be 2. Dang it, why did I do that? So that would have been 2. And then I'm going to add 1.5 again and get 3.5. And then I add 1.5 again and get 5. All right, so there's our first 5 terms. I need one more, 6.5. There's our first 5 terms in that sequence. Next one, we want to find the first 3 terms in this sequence. So this is a geometric sequence because of this nth power right there. So if I'd put a 1 there, -8 to the first power is -8, and then multiply by 1/4. Multiplying by 1/4 is the same thing as dividing by 4. So I've got -8 and then divide by 4, so that's -2. Next, if I plug in a 2 here, -8 times -8 is 64, and then I'd multiply it by 1/4 or divide by 4, which would be 16. The third term is -8 to the third power. Now that's -8 times -8 times -8. Since there's 3 negatives there, that's going to be a negative answer. I think it's -512. 8 times 8 times 8, 512. So that's -512. And then I'm going to multiply it by 1/4 or divide by 4. And if I divide by 4, I get -128. So that's the third term in the sequence. Next, we want to write an equation using the A of n notation. So this is just like T of n. We're just doing A sub n on this one instead. So using that notation, I'm assuming they mean a explicit sequence, or an explicit equation. So I'm going to say A of n is equal to, now what's happening here? It looks like I'm multiplying by -1. So what we need to do for this type, if it's a geometric sequence, is we do A of n equals the starting value, so A of 0 is the 0th term, times B ends up being the common ratio to the nth power. So I'll just write that down here. So A of n equals A of 0 or A sub 0 times the common ratio. I call it R, why do they call it B? And then to the nth power. All right, so the starting term, so since we're multiplying by -1 this way, I've got to multiply by or divide by -1 going this way, which is the same thing. So this will, our starting value will be 4. Remember, the starting value is the value that doesn't actually show up here, times -1 to the nth power, because our common ratio is -1, because we're multiplying by -1 each time. And then we can plug in numbers to see if it works. First power would be -1 times 4, -4, that is our first term. Second power, -1 times -1 is +1. So 1 times 4 is 4. See, it's working. All right, next one. So for this one, it looks like, what am I doing here? I'm adding 6 each time. I am. I'm adding 6 each time. So this one's arithmetic. So when we use the arithmetic sequence, our notation for this one is going to be A of n equals m times n plus A of 0. So this is the common difference. This is all going to be pretty much what we've been doing with the T of n, just using A of n instead. So A of n is equal to the common difference of 6 times the term number plus the starting term. So the starting term is not 7. We look for the 0th term. So we're going to subtract 6. So the starting term would be 1. There we go. All right, next part. Janine was working on her homework, but she lost part of it. She knows that one output of this is 78,000, but she can't remember if P of R is a sequence, if it's a function, or if it's both. Well, this is exponential, so it's definitely going to be a function. I'm going to say it's a function. Is it a sequence? Well, if it's a sequence, we should find an R value that's an integer that works for this one. So let's set it up kind of like what we did before. We're going to say, okay, P of R, what if that were 78,000 equals 2 times 5 to the R. All right, I'm going to divide by 2 on both sides. So if I divide by 2, I should get, what's that, 39? So if I divide by 2, 78,000 divided by 2, I get 3,900. Sorry, not 100. All right, and now what we should check is there a power of 5 that is 39,000? It's not, because it always ends in 25. So we can just double check it though. Let's try 5 to the, I don't know, 6th. Okay, 5 to the 6th doesn't work. Let's try 5 to the 7th. Well, now that's beyond 78, so no. The actual exponent would be between 6 and 7. What happened there? So the actual exponent, since 5 to the 7th is 78,000. Oh, wait, no, we're looking for 39,000. Since 5 to the 7th is 78,000, that's too much, and 5 to the 6th is 15,000, that's too little, then no, there is no power of 5 that where I have an integer that it's going to be equal to there. So this is just a function. Because the answer for r that makes this work is not an integer. All right, last thing, we're going to pull up Desmos real quick, and we're going to see if we can solve for x on this function right here by just looking at Desmos. Now, what's interesting here is this is our y value, right? So this is like having the function y equals 200 times 0.5 to the x power. Okay, so what we're going to do is plug in Desmos, find out where y is equal to 3.125, and then see what the x value is right there. Okay, so let's pull up the Desmos. I think it's this one. All right, so let's go ahead and get rid of this. So we said y equals 200 times 3 to the x power. So 3, and then I do a to the b, 3. Why did it do that? To the x power. All right. So we've got 300. Oh, it's 0.5. I'm really messing up today. 0.5 to the x power. To the x power. All right, so we said that the x value should be 3.125. So 3.125, somewhere around here-ish. So let's go to the graph. Now on Desmos, it's kind of nice. So look over there where we've got the x value is 5.96 and it's 3.213. So let's go down a little bit. 3.2, I want 3.125. There we go. Oh, go back. Please, be nice to me. Ah, there we go. So the x value there is 6. So you can actually use graphs to solve these. If the y value is 3.125, this says the x value should be 6. All right, let's go back to our paper here. So I used the graph. I found out that on the curve here that we had 6, 3.125. So x must be 6. Because y is 3.125, and according to the graph, x would be 6. All right, let's do the same thing on the next one. So we're going to use y equals 6 times 3 to the x power. And y is going to be 318 for this one. All right, so 318. Let's find out where the graph says the x value should be. All right, last problem of the semester. Let's not mess it up. Holcomb. All right, so here we go. We're going to do 6 times 3 to the x power, 3 to the x. All right, so we said we wanted the y value to be 318. Oh, goodness, that's way up there. Let's zoom out a little bit. All right, so we want it to be 318. There's 200. There's 300. Let me zoom in a little bit right here. All right, so here's my graph. Let's get in a little bit closer. All right, I want it at 318. So I'm going to click on my graph here. So watch your x value. We're at 317.3. Let's see if it'll give us our exact answer. Oh, that's as close I think as we're going to get. So it looks like when the y value is 318, the x value is about 3.61 or 3.6. We'll just call it 3.6. So using the graph, I know that the y value is 318, so the x value for this function must be 3.6. So you can use your graphs to solve equations. All right, so the x value was about 3.6. So to solve this equation, x would be about 3.61. And you can actually plug that into your calculator if you want to. You could do something like 6 times 3 to the 3.61 power. Why is everything not working today? So 6 times 3 to the 3.61 power. 316, so we'd need to be a little bit more, 3.64. 6 times 3 to the 3.614. Yeah, there we go, 614, we'll call it. So x would be the 3.614. Awesome. Yay, math. All right, math hard. We're all done. I'm tired. It's time to go home. See ya. Bye-bye.